So very pleased to introduce Aaron Courville here, who I've followed his work for a long time. He's been doing deep learning and machine learning things before that are all very interesting. And today he's going to talk about a new generative model for speech.
Thank you. So I'd like to thank the organizers for inviting me. It's both the coolest room I've ever given a talk in and the only time I've ever had a session of Aaron's, which is fantastic. So I'm very excited. Let me just get started. All right, so this talk is a little bit unusual for me. I actually don't get to talk about this stuff very often. I talk mainly about generative models for images and some other work I've done. And so I'm going to mainly the way I'm going to do this is I'm going to talk a little bit about our work on, well, quite a bit about our work on speech synthesis, our efforts towards end-to-end speech synthesis. And then I'm going to talk a little bit about some other things that I've been doing that I think are relevant to you. It might not seem immediately so, but I think it's new work that we've done that I'm pretty excited about, and I think I think it'd be very useful for this community to see it. All right, so first up, audio is a very challenging area. We've been actually at it for a very long time, a rather embarrassing amount of time without a whole lot of progress. This is one of these areas where we were just kind of beating our head against the wall for a long time. And it really has to do with this issue here, which is that the structure is, you have a lot of structure at very different timescales. This is not something I have to tell this community, but but it makes it very difficult when you're trying to model it for synthesis, because you've got to model it very locally to get the sound quality right. And then if you want it to say anything reasonable at all, you have to model the very long-range structure as well. So you have to kind of get it right at every level. It makes for a very challenging task from a generative model point of view, because you can't kind of cut it at any point and say, okay, well, I'm just going to assume independence from this point down. So this sort of motivated our work in just trying to get the low-level problem right first. And this is what we came up with, which is the sample RNN. So this is, I'm just kind of jumping right to the model structure here. This is the model that is going to essentially model the low-level structure of our end-to-end speech synthesis model. So we've basically handled at least the low part of this long-range structure problem by using different tiers of RNNs. So at this bottom tier, this is the sample level. So each sample here, each unit here represents a sample from the raw acoustic signature. And then this is literally the number we have. We have 4 of these. And then we bump it up here. And then we have another tier 2 here, which has a set of units here. And each of those get bumped up to this tier 3. And tier 3 is an RNN that's running at a much higher time scale. It's like 16 times, roughly, in this picture, the low levels time scale here. And so by modeling things at this kind of multi-time scale way, we're actually able to get much better performance than we had up till now. So that's the structure. If we look at the kinds of things that we can generate, so at the top row here is the real data. This is for a few different data sets here. We have Blizzard, onomatopoeia, music, and what I'm showing in the middle and the bottom row are just two different versions of our model. So the one in the middle here is the 2-tiered version. If I go back, it's the one without this top tier here. It just has this middle tier. So there's 2 levels of abstraction, let's say. The bottom one is this full 3-tiered model here. So looking at these pictures, I don't know. I don't certainly notice much of a difference between the two. Maybe you guys do. But we can hear a difference if we play some sound. Actually, what I'm going to be playing for you now is, I think, both 2-tier and tier 3. So this is, you know what, I've forgotten if this is tier 2 or tier 3. But for music, we'll see that it actually doesn't make a big difference, and people actually seem to prefer the 2-tier model. So this is, by the way, what I'm playing you now is just completely unconditional music. So it's trained on piano music, and now we're just letting the model run. And this is what it comes up with. So it doesn't have a great deal of structure to it. This is because it's completely unconditional. We can do the same thing with speech. And we get. So this is unconditioned speech. So it's not given anything to say. We don't give it text. We don't give it words. So this is what it comes up with. So prosody is there. It has different kinds of emotional range, but it's not saying anything. It's gibberish, right? So this is exactly the kind of problem that we want to fix. But before we get into that, I just want to finish up with this. So this is kind of the local structure we see with our model, 2-tier versus 3-tier compared to the real data. It's actually getting the low structure fairly well, especially on with the tier 3. You can see that there's still a little bit of noise compared to the real data, and you can actually hear that when you play this thing. That's one of the problems of our model is that, I mean, it's possible that we just haven't trained it long enough, or that we haven't used enough data when training, but you can actually perceive there is a definite noise. So related work, as was mentioned, there was around the same time as our model came out, the Wavenet architecture came out, which is here. So we compare ourselves to our implementation of Wavenet, and I'll get to those numbers in a second. But just to compare at a high level what those are. Actually, well, I'm not going to go into too much in the Wavenet architecture because I think Aaron's going to describe this next. But it's a very clever architecture. I'm actually a big fan of this model, especially for this kind of data. So it's basically using a dilated convolution here, where it looks at sort of different scales, and it sort of subsamples at different scales, and that's to generate the next sample. But if we sort of compare and contrast our model versus theirs, our model runs at different tiers. So every tier runs at a different time scale, whereas in Wavenet, all the tiers, essentially, all the levels or layers run at a lockstep at the same low-level resolution. For the sample RNN, our model, we can keep and use information from an arbitrary past because it's an RNN. Whereas the Wavenet, it's a convolution-based model, so it can only deal with information from a limited receptive field. Now, the other difference is that our sample RNN, we cannot parallelize, or at least we cannot easily parallelize because it's an RNN, right? There's this fundamental sequential sampling process involved. Whereas for Wavenet, it's fully parallelizable since it's basically based on a ConvNet, and when you're training with teacher forcing, it's fully parallelizable. And to be honest with you, I would trade the rest of them for this feature here because it makes a huge difference that you can parallelize it and train it at scale. So like I said, I'm actually a big fan of the Wavenet architecture. Now, okay, so for this, we've compared our results versus a standard RNN model, which is just kind of a one-tier version of the model, against our implementation of Wavenet. At the time, this is the best we could do with Wavenet. We were very interested in this model. This is the best we could get. I'm not saying that this is a fair comparison against the Wavenet model implemented at DeepMind, but I will point out that DeepMind does not release code as a general rule. I wish they did. It would make comparisons like this much easier. So this is my public advertisement for sharing code, and please do it. Okay, so human evaluation. So what we did here is we just asked a few people, just because it's very difficult to evaluate the quality of these things. So with the speech synthesis model, this is trained with Blizzard. We asked for a pairwise comparison against these models. It turns out that pretty much across the board, the 3-tier model was preferable. Again, all of these models were essentially preferable to our version of Wavenet. Don't take that seriously as a slight against Wavenet. It's just our implementation of it. But yeah, so in 3-tier was essentially for speech, was definitely preferred, with the long-range structure being more clearly evident in the 3-tier model compared to the 2-tier. If we compare on music generation, the story actually changes. The 2-tier model here is actually slightly preferred. I'm guessing, because we didn't do a very detailed analysis here, but I'm guessing the reason why the 2-tiered model was slightly preferred here is only that for music, at least the kind of music that we're talking about, the long-range structure is a little bit different, and what these users were really picking up in is just sort of the very, very local structure of the sound quality, right? How noisy is it, what kind of local structure it has, and so the 2-tier model was enough to do that, and maybe it was just slightly preferred for that reason. All right, so key components of this sample RNN model which are important to make this thing work. We quantize the output. So the raw signal is quantized into 256 bins. We use a multinomial to model that. Adding more tiers helps with the RNN. And autoregressiveness is actually really, really important, especially at the low level, to make this work. What we had tried for almost a year before making this work was a model that actually output independent time steps at the lowest level. And that just did not work. It did not work very well at all. So the autoregressiveness for us is really critical. And at generation time, Wavenet shares that autoregressiveness. And finally, we use an embedding as the input at the sample level, also improves the results. All right, so that's going to be our low-level model and what we're considering next. We're going to call this the neural vocoder in a second, and I'll tell you why. But now I'm just turning to, actually transitioning to a different paper. This is our char-to-wave paper. And our goal here is to output speech, output a model that does text-to-speech, right? So the idea here is you give it some text, and maybe you give it random noise, or you give it some sort of randomness, and it's going to go through your deep neural network, and it's going to generate samples. Yeah, something like this. All right, so what our model architecture looks like is what's shown here on the right. So it's a combined model. So as I mentioned before, the long-range structure is very severe as an issue, as a challenge for these kinds of models. And what we've done here is we're actually leveraging vocoder data and a vocoder representation, which is kind of we're taking it as an intermediate representation. So we've broken our problem up to sort of break up this difference in time scales, because our sample RNN only goes so far, and you can see that that's what's represented down here at the bottom level. Right here is our vocoder, is our neural vocoder. And then above this is this vocoder feature layer. And what we're going to do is we're going to use the world vocoder to transform our data and kind of break it into these two pieces. One that's going to learn a model that goes from text to vocoder features, and another one that's going to go from vocoder features down to the audio. And that bottom level is going to be the sample RNN I just talked about. The top level, we're going to use a different model. We're going to use a model, that uses attention. So this is essentially our RNN with attention model. And this is really the sort of the guts of our char-to-wave model here. And the model we end up using, actually, we converge to something very, very similar, in fact, trivially similar to Alex Graves' model for handwritten recognition. It's basically the same structure, where we use attention here over this model. So this part right here is essentially it's attending over hello here, and it basically, we're using the soft attention mechanism to do the alignment for us. Because what we really have is a problem when you talk about these different time scales. We have this alignment problem between the characters at the top and the vocoder features at the bottom. So different sets of characters are going to align differently to different vocoder features. And so we're using an attention mechanism to do that for us. Yeah, so that's the structure of our model. We're going to now training this model. Oh yeah, so before I get into training, so the problem here with the structure that I'm describing here is that when we train the top level model, which we call the reader, the first time we tried training this, the first few times we trained this, we've noticed this problem, which is when you train this with teacher forcing, you have this problem that it basically, there's so much correlation, even at this time scale, there's so much correlation between time steps that the last sample is really almost all you need to predict the next sample. So there's not a lot of gradient signal to train the attention mechanism. So the way we got around this is we just injected noise, basically, into that feedback of the previous sample. And then we annealed this noise as training continued to allow the top-level attention mechanism to train. It's, maybe not super elegant, but it worked fairly well. Be interested in exploring other mechanisms to alleviate this issue. Right. So our training then was basically broken down into 3 steps, or 2 steps concurrently and then a third. The first step is we just train the reader that we described, which maps from text to the vocoder output. Then we train the vocoder output, the vocoder representation to the raw audio output, and we train these 2 pieces separately. And this is actually pretty important because the amount of text we can learn when we break it into these 2 pieces is much greater than if we were to train the whole thing together, because the number of samples we need to process in our RNN at the low level is very large compared to what we would process at the top level. So in order to train our reader sufficiently and with enough data, breaking this up in these 2 pieces was very useful. And then finally, we fine-tune the whole process together to sort of get the match. And all of this together is our char-to-wave training scheme. All right, so what advantages does it have? It has no handcrafted features as described. It's easy to change the language. It's very flexible. Disadvantage is it's limited somewhat by our reliance on this vocoder. And if you like, the fact that we're leveraging this vocoder in training is a little bit like using handcrafted linguistic features. So this is one of the areas where, moving forward, I would like to remove our dependency on this vocoder. But one thing is that when we turn to English, we actually have a bit of a problem, which is that our model just didn't actually work very well going from characters in English mapped to the vocoder features. So what we did instead is we actually used a pronunciation dictionary, which is misspelled, but we used a pronunciation dictionary to map from, instead of using characters as our dictionary elements, we use phonemes as our dictionary elements, and then we map from there. I'll just play you now a bit of the difference between these two, why that was important. And it's basically because in English, characters are a very bad representation of the way things are going to be pronounced, right? It's a very complicated mapping, and our attention scheme was already having to do this alignment. Combining that with this issue of this kind of misalignment didn't work very well. So this is we have a kind of a website, so I can go down. I'll get to Spanish in a second. Turns out Spanish is much easier. You can train right from characters with Spanish. So if we go to English, yeah, so this is what you hear when you train it on just characters.
He was a crazy man. It's a source of deep concern.
Okay, so not very well pronounced.
He was a crazy man. It's a source of deep concern.
That's the difference. So just this is with phonemes, trained on phonemes.
It's a source of deep concern.
Versus training on characters.
It's a source of deep concern.
Let's see, crazy man on phonemes.
He was a crazy man. He was a crazy man.
So that's basically the. If we talk now about Spanish, because Spanish is basically essentially maps very easily from characters or from the written word to the phonemes. It actually we were able to easily train this model directly from the characters. So to give you a sense of what that sounds like.
México dispuesto a fortalecer sus relaciones comerciales.
So I don't speak.
Los objetos del proceso pueden estar afectados o no por el mismo.
I don't speak Spanish, so I have no idea what they're saying, but it sounds pretty convincing. Oh, sorry, these are the originals. That's why it's yeah. Okay. Hold on. Okay, let's hear the okay. Oh wait, sorry. That is that's a vocoder output. So let's go the full chart-to-wave model. Okay, so still pretty good, but you can hear there's actually a little bit of noise added, and that's really at the low level. So it's interesting. The chart-to-wave. This is. Okay, here's what happens if you just take the reader, which is our top part, outputs the vocoder representation, and if we just give that to a vocoder, this is the same thing. Okay, that's good.
Una síntesis más global acerca de la cual no sabía nada en esa época.
Okay, so if you hear this, if you sort of, I guess, listen to these very carefully over a while, what it sounds like is that the vocoder output is actually a little cleaner. The noise goes away, but it's more robotic, more flat. Whereas the chart-to-wave model gives you a little bit more dynamic range, but it also adds noise. Okay. All right, so returning. So that was the Spanish to text. So like I said, we could learn this model directly from text in Spanish.
Los aumentos en el costo de energía
another.
Okay.
We took an early version of this model. This is for the submission. We haven't actually redone this on our newest examples. They're the ones that you just heard. It turns out that with the older version, the reader was preferred with the decoder output compared to our chart-to-wave model. And so really what this comes down to is, I think at the time there was a little bit more noise. And I think what we saw is that when asked to judge preference, readers preferred something that was cleaner rather than something that was noisy. It's just a question of, do you prefer flat, noiseless output or sort of more robotic, or noisy, more dynamic output? And this seems to be what people preferred, at least in an earlier version. And a similar sort of story happens when we look at the intelligibility. So yeah, so the character wave, there was more error rate. So the test here for human evaluation is we just had people listen to it. This is in Spanish, so we had native Spanish speakers listen to the audio and then transcribe, and we measured their accuracy, their word error rate, and this is the results we see. Okay, and there's actually related work from Google. The Tychotron, again, came out sort of a similar time. A very impressive model. The difference here is they use Griffin limb reconstructions at the output rather than going directly to the acoustic domain output as we do with our sample RNN. Okay, so one of the things that we did next with this work was we were interested in looking at some of the latent factors that were involved. So what we were kind of interested in doing is seeing what we can do to manipulate voices to the audio. So it was enough that we could sort of emulate the audio of what we trained on, but we wanted to sort of change the voice of the person on the fly. So this is the kind of things we did early on, our early experiments with this kind of thing. This is the kind of thing we got.
All who can distinguish will understand your motive.
That's the original, and that's the ground truth. And now I'm going to play you a few different samples of our model synthesizing this with sort of changing the voice through this latent variable model. So what this was is basically we tacked on a kind of a variational autoencoder to this model. We inferred Z, which represented the voice of the speaker, and then we just started manipulating this voice. So this is the kind of variation we heard.
All who can distinguish will understand your motive. 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 All who can distinguish will understand your motive.
So this one clearly just changes pitch, and for something pretty creepy.
All who can distinguish will understand your motive.
That's just all of them combined. Okay. Yeah, so that was kind of early on in this process. Now, the students that were working on this project, in fact, really the core of the group working on Chart a Wave, got pretty excited by this problem and thought they had a bit of a niche. So they went and founded their own company, Lyrebird. These are three of those are students that did this. The Jose was the first author on the Chart a Wave paper. He's, by the way, a Mexican, so he's a native Spanish speaker. I think that influenced his choice of experiments. Right. So I'm going to play you a little bit of what they've done with this now. So they really took this idea of changing the nature of the speaker and sort of the kinds of things you can do with this, and they got a little bit of press for doing this. It was kind of fun in the era of fake news. So this is the kind of thing they've come up with.
This night I'm happy to share with you a small announcement about a cool startup called Lyrebird. They launched today their website where you can create a digital copy of your voice. They only need you to record 1 minute of audio. This is just the beginning, and they are working hard to improve their results. They want to use this technology to change the life of everyone that lost their voice to a disease by helping them recover this part of their identities. Let's help them achieve this goal. You can help them testing their software and sharing this video with your friends.
So yeah, so they also did the video. It turns out it was actually pretty simple to do the video. They just used L1 reconstruction to make that work. One issue with actually this point that he made at the end of sharing the motivation for this work being that to help people who have lost their voice. So that I don't know if they really started out with that kind of a goal, but it turns out that when they got the press, when they sort of first introduced this work, they actually heard from all kinds of people. They heard a lot from journalists as well, and thinking about fake news and the kind of manipulation you can make, but they also heard from just normal people that have these sorts of issues and wanted a way to preserve their voice and be able to, because somebody, for example, was going into surgery to remove their larynx, and they were worried about like losing their voice forever, and they were recording their voice, and so in order to preserve it with a method something like this. There are other people with maybe more disturbing requests as well, but anyway, so other people sort of started having fun with this kind of technology. So this is probably my favorite. So this is somebody that just posted something on Twitter. So wow, it turns out Lyrebird is really good at making sarcastic howl voices howl from 2001. So we can hear that with that sound.
Open the pod bay doors. Now stop draining all the oxygen out of the base. That's what you sound like. I'm a stupid human that needs to breathe. Stupid flesh sacks that need like food and stuff.
Okay, so anyway, kind of fun. And there's a whole bunch of things on their website. They have conversations between Trump, Hillary Clinton, and Obama, so good fun. They're still not, I don't think, really at the point where it's indistinguishable from normal voices. You heard with the Obama clip. It's good, but it's not. It's distinguishable from the true voice. So I think they're sort of on that way, but I think there's actually some interesting work to be done before that's actually achievable. And of course now others are sort of getting into this space. This is actually a recent one, like IBM, that's sort of going into this. All right, so I guess now what I'd like to do is talk a little bit more about kind of like where we would like to go from here. And one of the things that we've been looking at, and this is not something we've really worked on much, but I think it's an interesting direction, is how do we overcome this long-range dependency challenge without relying on this vocoder representation in the middle? And one of the methods that I think could really help us is actually generative adversarial networks, and in particular, maybe something like CycleGAN. I don't know how many of you know CycleGAN, but it's a really interesting method, and I'm very excited by it. So CycleGAN basically works by having essentially training a transformation that goes from one domain to another with completely unpaired data. And I'll show you some examples in a minute. But the basic structure here is you imagine you have this G function that maps from domain X to domain Y, and an F function that maps from Y back to X. Now this so far, this mainly works well when these two domains are really within the same modality, but it'd be an interesting thing to think about going cross-modal with this and like very different kinds of data. So the way it works is, the way they're able to make this thing work with unpaired data is they have this cycle consistency loss, which is just this L1, which means that when you take something in domain X, you transform it to domain Y, and then transform it back to domain X through like a transformation with G, and then a transformation back with F, and that has to reconstruct to be close to the original in an L1 sense is what they use. And you do it the same way, going from Y back to X and then back to Y. Just those three pieces when combined, and so then you have like a Gann basically in both domains independently, so that when you take some sample from X, transform it to Y, that has to be a convincing example of something from Y. So that's how this thing is trained, and this is the kind of results you see. This is just taken from the first page of their paper. So my favorite example are zebras and horses. It's a very compelling example. So this is completely unpaired data, right? It would be very difficult to come up with this kind of transformation by finding paired examples of horses and zebras that just happen to be in exactly the right pose, right? That's not very realistic. But using this kind of completely unpaired data, they're able to train this model and get this kind of result. So it's not perfect, right? Like what you end up with is more like something like zebras that are horse-colored and horses that are zebra-colored. But still, it's very compelling. And I think there's interesting work to going beyond this in this direction. So anyway, I think using this kind of method for trying to think about how we map from, or how we can maybe chain a few of these transformations together to go from text to audio might be interesting. And then we can train these pieces completely independently because they don't have to be paired together. And they just have to match in terms of distribution. That's sort of the Gann magic here. So then we could just train these models up completely in parallel and use the appropriate amount of data at every level. So that's the kind of strategy we're looking at for something like this. We don't know if it will work. It's probably going to be much more challenging than the actual CycleGAN, but we'll see. So another thing I'd like to talk about, and this is what I'd like to spend the rest of my time here with you on, is something called, it's gone by various names. We've kind of renamed it a couple times, actually. But the first instance that I know of is called conditioned instance norm. And it was done by a student of mine while he was interning at Google, Vincent Dumoulin, who is the first author on this paper. So this is basically work where they've taken the same model and through this kind of transformation, this kind of architectural feature that I'm going to talk about, they've been able to map a single image, like say the picture of the woman here, through different transformations from different artistic styles and map to the same image, basically. So retexturing, if you like, this image through different styles. So this is the nice thing about doing deep learning. This is one of the reasons why I love doing deep learning, is that you can find a particular architectural feature, like something like this, and be like, that would be useful in all kinds of different domains. And suddenly you'll find that it is, and this is how progress happens so rapidly in this area, because innovation in one field and one domain transforms easily across domains. And it's pretty remarkable. So what we did is we took this particular feature and we applied it to a very different kind of task. Not reasoning, but reasoning. And we did this with what's called the clever data set. So this is an example of the clever data set. So this is this kind of a diagnostic data set. It's entirely artificially driven. It was rendered with Blender. So these are rendered images. The questions come from a set of scripts, but it's a pretty complicated set of scripts with a set of combinations that is actually quite large. So this is the kind of thing we have. So this is essentially visual question answering kind of task. So what number of cylinders are small purple things or yellow rubber things? Anyone? What number of cylinders are small purple things or yellow rubber things? Two. I see 2. Okay, 2. There we go. Yeah, so the materials I think are rubber and metal, basically. Those are the materials there. Yeah, so this is the nature of the kinds of tasks we have, and they have all kinds of different types of questions. They break down in terms of the nature of the questions. Are they asking you to count, like this one? Are they asking you what color it is, what shape it is, what size it is? Yeah, so there's all kinds of different kinds of questions we see. The way that this kind of model was previously done was using basically the best performing models with this kind of thing were using a lot of prior information about the nature of the task. So this is an example we pulled out. We were actually largely inspired by this. We thought this was a very cool model. But this is one where they essentially they break down the problem and say, to do this kind of visual reasoning, we need to break it down into a series of steps. And then they modeled each one of these steps, these kind of processing steps as a little neural module. And then they kind of dynamically reconstructed these neural modules together to do the prediction. But to do this, they need to go through this middle component, this predicted program component here in the middle. And for this, they actually needed to know the program labels to train this model, because otherwise they don't have the kind of information you need, because this is a discrete quantity and they're using reinforce to train this thing. So reinforce is just too high variance to actually train this thing in an end-to-end fashion. So instead, they do this middle component where they predict this middle step, a little bit like we did with our chart of wave, where they predict these discrete program labels, and then they fine-tune at the end using reinforce. But either way, this is using extra information in these program labels. So this is the kind of work before. So what we did is we took this idea, this condition instance norm that Vincent Dumoulin came up with, and it's actually related to a lot of other things in the literature at this point. And we basically constructed a model that was going to solve this problem, and it is a much, much simpler structure. So we have just a GRU. This is just like an RNN, kind of our local version of an LSTM, that takes in the question and then projects to these essentially what are essentially batch norm, if you're familiar with batch normalization. These are batch norm parameters that normalize, that are essentially the output of the normalization process, right? So you normalize, and then these in normal batch norm, these are just parameters. What we've done is we made them a function of the question. And so here in the middle is just a standard ResNet pipeline that takes the image as an input, goes through the standard ResNet layer, a set of ResNet layers at the beginning in the CNN part, and then goes through this part that gets modulated by the question. And it's modulated through this use of these batch norm parameters that are, again, functions of the input. So you see over here, you have the input comes in. The input comes in here, and then there's an element-wise product. Its film stands for feature-wise linear modulation. So there's a scaling here that's feature-wise, so which means that we don't actually need a whole lot of these parameters, because there's a single parameter per feature map, and the product is made across the entire feature map here for the convolution. And then we add a bias here, which is this thing, again, per feature map. So this is an operation that happens per feature map. So the number of parameters we're adding is actually quite small compared to the normal visual pipeline. So this is the model. And this is, again, just a little bit more in detail about the feature-wise linear modulation and what it looks like. It's a very simple function. It's just linear. It's a scaling and a shift, basically, is all it is. And we apply this in a feature-wise way. And this is the kind of accuracy we get with it. So the interesting point, so this is us here, and this is if you don't use pre-trained CNN at the bottom here. The highest performing number, this one right here, comes from when you use actual ImageNet trained resonant features here. But there's a lot of examples in this data set, so we don't really need that, and we get roughly the same performance if we don't use that. But what's interesting is this model has very little in the way of prior knowledge about the task at hand. It's essentially, we've not used very much at all in terms of the details. Unlike these two comparisons here that are sort of in the same ballpark as us, both of them use very much sort of a much more of an applied sort of, we are tackling this problem, and the approach that they take is very much, uses more prior information. And it's just essentially the use of what I view as kind of an elegant architectural feature seems to do very well in this case. So the reason I'm bringing this up is because I think film is actually a really interesting architectural feature that I think could be pretty, well, we have found it useful across a range of tasks, and we're using it right now in generation models, in particular image generation models, but I think it'd be useful across the board. This is actually an interesting thing. So I mentioned earlier that the kinds of models that we're comparing to here use these kinds of decomposition of the task, and first, we didn't go into it, but the first lower level things, the first thing you do is you filter on like material properties, and then at the top you start looking at more like question specific features. If you do a t-SNE decomposition of the kinds of filters that come out, you see that they cluster in very interesting ways. At the low level, which is on the left here, the clusters that you find tend to be clustered around these low-level features. Like, say, if we look at the cluster on the bottom, 12 and 4. If you look 4, query material, 12, equal material. So it's clustering around material properties, 7 and 10. 10 equals shape, 7, query shape. So it's basically clustering similar questions, but about certain things, right? Like, are we looking for colors? Are we looking for shapes? And then at the high level, the clusters flip around and now are more, what they tend to cluster together are whether they're equal questions, whether they're query questions, these kinds of things. So it's much more question specific. So we're essentially kind of discovering this hierarchical decomposition, if you like, of the task that was present in the models by Justin Johnson, for example. This model is actually learning that in an end-to-end fashion without any of these program labels. So we thought that was pretty interesting. This is just showing what these gamma, the scaling and shifting parameters look like. The scaling parameter is spiked at 0, whereas the beta parameter is sort of in the negative, which suggests to us like what these things are really operating like is a bit like essentially they turn off feature maps. So you have a set of feature maps. If they're not relevant, probably what we think is going on is that these things essentially just turn them off. And so you're left with a set of feature maps that are relevant for that task. We've actually applied this. So one of the criticisms you could level at Clever is that it's completely artificial in the sense that the questions are generated from a script. So we don't really have a good sense of how complicated those questions are. Maybe this is actually a very simple task. It certainly seems that way. People have gone from, relatively, if I back up a little bit here, this is the performance we got. We essentially started, I think we published this result around the same time that the Clever dataset was officially made public at CVPR for the first time. So just the rate of progress that we see in this field has been pretty impressive. And so some people take this as, well, maybe the Clever task was just super simple, and maybe that's all we're discovering. But so one of the things that's interesting is they also included something where they've asked humans to generate questions that were supposed to fool the machine. That's the kind of instructions they were given. So this is an example of one of those questions. Which shape objects are partially obscured from view? So the answer is sphere. This is an example where the model got this right. And the underlined sentences, underlined words there are ones that don't actually appear in the original Clever data set. So so we can see here that if we compare our method versus the previous ones that have been compared on this, we actually do pretty well just when we just do a transfer from Clever, but of course it's not very good because there's a lot of words here that we aren't able to adapt to. If we're allowed to fine tune, we do much better. But of course there's actually relatively few examples in this training set, so we're not really able to scale very well. But yeah, so we're essentially at state of the art on this particular task as well. And also this is something that's relevant. These kinds of methods have actually already been applied to speech recognition. This is a paper that came out of out of Mila in collaboration with Samsung, where they use this to essentially do speaker adaptation. So in this case, one of the things that's unique about what they did is it's essentially kind of a self-modulation. So the input itself modulates the acoustic pipeline rather than having side information like we use on Clever. But these kinds of architectural features seem to be popping up everywhere, and they're quite popular and quite effective. So yeah, so if I just back up a second and talk and just summarize what we've done. So Chart-A-Wave is our first attempt at an end-to-end speech synthesis system. It relies on prior linguistic information. This is something we'd like to overcome. Current performance is limited by the challenges of training with non-aligned text and speech. Our real challenge is overcoming these long-range dependencies. We think going to something like a Gann, or maybe particularly a cycle Gann, might be an interesting strategy to try to do that. And also just an advertisement for recent architectural innovations, such as this film-type modulation, I think is an exciting development that will have impacts in a wide range of tasks, in particular for you, speech tasks and music. All right, thanks, that's it.
Did you compare the film architecture to other ways you could try to take the information about the question? And
yeah, we did. There's a recent archive version that does do an ablation study, and it turns out that everything helps a little. You can do very well with just the shift. You can do very well with just the scale, but you do a little bit better with both. There's a lot of papers out there that just have one or the other. So yeah, I mean, the best thing to do is just go. It turns out also so what we did, if we go back to the, anyway, we've lost it. We applied this thing at every layer for a series of layers. It turns out most of the advantage can happen from just one layer. We do very, very well if we just inject it in one place. I doubt that's going to always be true. I'm guessing that there are certain tasks that would require more than one input for these things. But yeah, so there's a fairly complete ablation study. We did all of the variants we could think of that were interesting, and that's in the paper. Okay.
Other questions?
First, very nice talk. Thank you. So you mentioned the difficulty of training from English text directly.
Yeah.
Do you think that's a problem of maybe lack of training data?
It could be, yeah. I mean, so that's one of the reasons why, for us, decoupling these models is so important, and maybe even relying on data that doesn't require any kind of alignment at all, right? Because then we're free to train on a very large amount of data, right? If we don't have any level of alignment that's required. So yeah, that's something that we're exploring. I don't honestly know. It seems to me like one of those things that could actually be very, very difficult. So we've initial experiments. So cycle Gann, when it first came out, so this is the direction I'm kind of thinking about this. When it first came out, it seemed a little bit like magic to me. Results are really impressive. We've tried sort of pushing on it a little bit in the direction of things that don't map at a pixel-to-pixel level very well, and it gets much more difficult to do something reasonable once you break that. So that's essentially the setting we're going to find ourselves in. So yeah, it could actually be not such an easy path.
Thank you.
Okay, well, I'll ask one follow-up to that, which is, so did you try fine-tuning after getting the end-to-end system with the vocoder parameters.
Yeah, yeah, we did. And it improves. It definitely improves when we fine tune. Yeah, for sure. In fact, it doesn't do very well unless you fine tune. There's like this mismatch, right? Because neither model is perfect at getting that. So when you fine tune, it actually helps quite a bit. Yeah.
So maybe with even more data and the fine tuning, it might.
Right. Except
you have to cover all the linguistics.
Yeah, we're right. But the thing is, too, you have this problem that ends up being a bit like to have long range structure means something different at the different levels, right? So to have enough data at the top level, you have to be really, really inefficient in training the bottom level, right? Because you go through like tens of thousands of samples at the bottom level, and that just kind of grinds training to a halt. So it's strategies to get around that is kind of what we're trying to explore right now.
Yeah, that's also a general problem for speech recognition.
Exactly, yeah.
Let's thank the speaker again.